In this example, we're told we have air flowing through a nozzle with an inlet diameter of 200 millimeters, a given initial velocity, and an inlet pressure and temperature. And we're told the nozzle exit diameter is adjusted so that the exit velocity is 700 meters per second. We're asked to determine the exit temperature and the mass flow rate through the nozzle. So let's go ahead and sketch this out. So the nozzle will look something like this. And we have some flow of air into and out of it. Our control volume will be the interior of the nozzle, like that. And let's just write down the information that we know. So we know the inlet velocity is 400 meters per second. The inlet diameter is 200 millimeters. The inlet pressure is 7 kilopascals absolute. The inlet temperature is 420 degrees C. Oops, let's write that out properly. And then the outlet velocity, we're told, is 700 meters per second. So in order to find the exit temperature, what we're going to do is apply the first law to that control volume. So let's write that out. The reason I'm thinking the first law is because what we have here is an exchange of kinetic energy into internal energy. So we're changing the inlet velocity and the outlet velocity, so we have a change there. So we'll expect that there'll be a change in the internal energy of the air as well. Okay, so if I'm going to have a change in the internal energy, it's really the enthalpy of the fluid, then I need to apply. And the first law is a natural relation to use for that analysis. So I'll write out the first law in terms of for control volume. So I'll just write the whole thing out here. And just a reminder for what each of these terms represents. This is the time rate of change of total energy within the control volume, so that's inside the dashed line here. This is the heat transfer coming into the control volume from the surroundings. This is the work done on the control volume. By the way, this is the rate of heat transfer, and this is the rate at which work is being done on the control volume by everything other than boundary work or pressure work. Here we have the flow of specific total enthalpy coming into the control volume. So it would be coming in, crossing the control volume surface here. It's total enthalpy. The total enthalpy, remember, is just the enthalpy plus kinetic energy plus potential energy. So this is the specific total enthalpy. And then we subtract out the specific total enthalpy leaving, or the total enthalpy leaving the control volume through the outlets, which would be right there. So let's go ahead and simplify our equation here. So first of all, we'll assume that we're dealing with steady state, so that first term is 0. I'm also going to assume that there's a little heat transfer occurring through these boundaries. So I'm going to assume that this is an adiabatic process, so that the heat transfer is 0. So I'm assuming it's adiabatic. That's an assumption. There is no work other than boundary work or pressure work here, so that's going to be 0. And then when we get to the enthalpy terms, we'll assume that the kinetic energy terms are negligible. That's certainly a reasonable approximation when you compare the potential energy to kinetic energy or the specific enthalpy. Especially when you're dealing with gases, this term will be much smaller than these other terms. So then what we're left with is the following. Okay, so this is our now simplified first law equation. Let's go ahead and apply conservation of mass to that same control volume, and I'll just write it out up here. So here's conservation of mass. Written out, this is the time rate of change of mass within the control volume. This is the rate at which mass is coming in through the inlets. the rate at which mass is going out through the outlet. So again, if we're dealing with a steady flow, so steady state, we only have one inlet and one outlet, so this will just be m dot in and m dot out. And so what we see is the m dot in is equal to m dot out. And I'll just call it m dot for convenience. So conservation of mass just tells us the mass flow rate through this nozzle remains constant. So when we come down here, this m dot in and that m dot out will cancel one another because they're the same. So now what we're left with is, if I just do some rearranging, it'll look like the following. Okay, so that is now our first law expression. Okay, so at this point, let's think about what we know. So we're dealing with air. We'll assume that the air is an ideal gas. If it's an ideal gas, then that means the specific enthalpy is a function only of the temperature. So the inlet specific enthalpy we can look up from a table because we know the inlet temperature. The velocity coming in, we know, that's given right here. The velocity going out, we know, that's given here. And so then we can calculate what the outgoing specific enthalpy is. And if we know that, then we can again use our ideal gas property tables to find the temperature at the outlet. Remember that for an ideal gas, I'll write it over here, for an ideal gas, the specific enthalpy is a function only of the temperature. Okay, so let's do that. So H in will be H at T in is equal to 420 degrees C. So I can use the thermodynamic property tables, and if you do that, you'll find this comes out to be 705.75 kilojoules per kilogram. So this comes from the ideal gas property table. Let's make sure we spell it properly. Property table for air. We know V in was 400 meters per second, and V out is 700 meters per second. So when you plug all those numbers in and you're careful about unit conversions, you have to be a little careful with the unit conversions here because you have to be careful. This will be meters squared per second squared, and you need to do that. You need to convert that over to kilojoules per kilogram. So just be careful of that. But anyway, if you work all that, you'll get the specific enthalpy out is 540.75 kilojoules per kilogram. And then we can use the ideal gas property tables, again, to find that the temperature out is 264 degrees C. Okay, so that first part is just a matter of using the first law and recognizing that for an ideal gas, the specific enthalpy is a function only of temperature. Then the other thing you have to be a little careful of is dealing with some unit conversions when you do the velocity squared and the specific enthalpy. Okay, so the next part of the problem is to find the mass flow rate through the nozzle. So to do that, I'll just find the mass flow rate at the inlet. It'll be the same mass flow rate at the outlet, but the reason I'm choosing the inlet is because I know the velocity there and I know the diameter. If I know the diameter, and assuming it's a circular inlet, since it's a diameter, it's reasonable to assume it's a circle, I know the area. And then if I know the pressure and temperature, I should be able to get the density from that. Okay, so let's go ahead and write that out. So the mass flow rate will be the density at the inlet times the velocity at the inlet times the area at the inlet. I guess I put in for all those. And the density at the inlet we can get from the ideal gas law. That'll be the pressure at the inlet divided by the gas constant divided by the temperature at the inlet. So this is the ideal gas law. The velocity at the inlet we're given, that was 400 meters per second. And the area at the inlet, it'll be the area of a circle, which will be pi diameter of the inlet squared divided by 4. And so we should have enough information here. We can then figure out what the mass flow rate is. I didn't actually write down the calculation for what the density comes out to be. All I did was actually just calculate the mass flow rate. When I do that, I get 0.44 kilograms per second for the mass flow rate. Okay, so I didn't actually do the intermediate calculation here. By the way, the gas constant for air is 0.287 kilojoules per kilogram Kelvin. That's a good number to memorize because we use it all the time. Okay, so for part A of this problem, it was a matter of applying the first law and then having some reasonable assumptions here: steady state, adiabatic, no work other than the boundary work, the inlet and outlet. A little application of conservation of mass at the same time, and then recognizing again that specific enthalpy is only a function of temperature, and then making use of the ideal gas property tables. And then to find the mass flow rate, it's just the mass flow rate is equal to the density times velocity times area. By the way, you could also write this as velocity over area over velocity times area over specific volume. That's another way to write that. So instead of finding density, you could find specific volume. And then being able to calculate the area just from the diameter. All right, with that, we'll just go ahead and end the example.